I had asked you several times.
Tried.
You have tried?
Tried.
Okay.
Yes.
All right. So let us see about other students, whether they have tried it or not. And then we will go ahead with the workings. All right. So
Ma'am, I had a doubt in the question.
yes.
When you say 3 gigahertz CPU with requirement of 200 clock cycles per instruction to process a packet, does that mean to process the entire packet it takes 200 clock cycles?
No. It should be, I think here the CPU is going to work only with the 20 bytes.
Okay, so it works with 20 bytes at a time.
Mm-hmm.
And since the IP header is only 20 bytes, so we can take it to be 200 clock cycle.
Yes, you can take it to be 200 clock cycles. Okay, so let me just start this. So yes, bus bandwidth. How do you calculate the bus bandwidth? So what do we know about the bus capacity? It's 133 megahertz, 32 bits. How do we get that bandwidth then? 133 megahertz, 32 bits. How much was this? Somebody said last time.
4.256 gigahertz.
Gigahertz, no? GBps, no?
Yes, ma'am.
Gigabits
Yes,
per second.
yes, GBps. Okay. Then what should be the IO transfer time from NIC to main memory using DMA? So after this, using DMA, there will be IO transfer from the network interface card to the main memory, right? So what do we know about this? We have a 40 byte packet. The bus capacity or the bus bandwidth is now 4.25 Gbps. This is byte. Now, what is the value?
$75.2 nanoseconds.
Everybody got this value, 75.2?
Yes, ma'am.
Yes, ma'am.
Okay, so then what is the time taken to send the packet through the bus? That is, okay, I wrote it here. All right, it's okay. This is the time taken, all right. Oh, just a second. Then main memory read time for IP header. So see there, it will be a read write, right? We know that RW will be there at main memory. So 20 byte header is that. So twice it will be there. So 20 plus 20, 40 byte RW will happen. All right. So here 40 bytes of data. Okay. Please do note that this is not the 40. Just a second. What is happening? Okay, just let me just do it in this way. So main memory read time, so we have 40 bytes of data now. So what is the main memory capacity, bus capacity is 800 megahertz, 32 bits. So now how much is the value?
25.6 gigabits per second.
Okay, how did you find this out?
800 megahertz into 32 bits.
Okay, so we have bus capacity here. All right, so 800 megahertz times, sorry for my writing here, my writing is not this bad. Okay, so 800 megahertz times 32 bits. So this is something 25 point something you said, right?
Yes, ma'am. 25.6 gigabits
25.6.
per second.
Gbps. All right. Then what should be the transfer time? You have 40 bytes of data. So 40, okay, let me just do it here itself. 40 bytes divided by 25.6 Gbps. Please remember, when you write in your exams, this units are very important. Do not lose out the units in each step. Okay. All right. What is the value for this one?
12.8 nanosecond.
Okay, 12.8 nanosecond. All right. Then next is IO transfer from main memory back to NIC. Oh, sorry, this I
No, ma'am.
wrote wrongly. This is
Yes, ma'am.
12.8 nanosecond. Okay. This one is not. This is time
2.5.
taken packet. Yeah. So process time taken to process packet. What it will be? We know that this is 200 clock cycles per instruction, right? And we have a 3 gigahertz CPU. So 200 clock cycles per instruction, and then 3 gigahertz CPU. So this is this. What is the value? What is the value for this one?
66.66 nanoseconds.
7, let me write, 66.7 nanoseconds. Okay. Now we will get IO transfer time back to NIC. Okay. So we have already considered, no? We have already found it. What is the time to move our packet from
Yes. 74
yes, this is
NIC to my memory.
right, we have got it, 75.2 nanoseconds. So this is 75.2 nanoseconds. Oof, why is this happening? Anyways, let me write it again. This is 75.2 nanosecond. Okay, then what is the total transfer time then? Total time to process the packet should be written like that. What is the total time to process the packet? That was the question. So first is our 75 nanoseconds
12.5.
plus we took time there for a memory RW. So there it was, I have written 12.8 nanoseconds. So
12.5, ma'am.
12.5. Why it is going? All right. Just a second. All right. Okay, so this is 12.5 nanoseconds. Oh, this is not working properly. Okay, let me just stop with the pen. So 12.5 nanoseconds plus again 66.7 nanoseconds, then 75.2 nanoseconds. So what is the total time that you are getting? Total time to transfer the packet.
229.6.
229.6. Has everybody else got this value?
Yes, ma'am.
Yes, ma'am.
29.6. Great. So 229.6 nanoseconds. Now the question is, how do we find out what is the switch throughput? What is the switch throughput? How will you find out?
Ma'am, 40 bytes by that transfer time.
40 bytes by the transfer time. So that is like for transferring, you are saying that for one packet, this one will be there, or how are you going to calculate this? I mean, how?
Every packet which is of 40 bytes, we need that much.
40 bytes by the transfer time, right?
Yeah.
Okay, so how much is the transfer time? 229 point something.
0.6 nanoseconds.
0.6 nanoseconds and 40 bytes. So 40 bytes divided by 229.6 nanoseconds. How much is it coming out? Meanwhile, I'll just check this part.
174.
I couldn't hear you. Can you please tell once again?
174. 174.2
174.2
megabits.
megabits.
0.2 megabits.
Mbps.
Megabytes per second.
Megabytes per second.
Bytes.
Okay. All right. So, what are the other students getting it? Can you convert it to some in bits or something? It's throughput now. So, can you just convert it to bits and give the result? I mean, BPS, Mbps, GBps, anything will do, but consider it into bits.
Ma'am, I have one doubt.
Yes.
Ma'am, here it is written that 200 clock cycles per instruction. So do we need to count all number of instructions or not? Means
No,
it is written per instruction.
as I was saying that here we are just assuming that the header is going to take just one instruction, and then that is how we are just calculating the time. So if you find out that this is the time that will be taken to just do the processing of the header. That's it.
Okay, thank you.
All right. If it is more than one instructions, then it will be told to you. All right. All right. Something else.
1.39 gigabits per second. Throughput, ma'am. Ma'am, your voice is breaking.
Am I audible to you guys? Am I audible?
Yes, ma'am.
Now you are audible.
Now I'm audible. Okay. So I missed, I mean, you guys must have missed some parts. Okay, let me just go back once. So I think throughput you could find out by just, you have 40 bytes of packet, and then the total transfer time is coming out to be some 228 around nanoseconds. So with that, you get the throughput to around 1.39 Gbps. So that is what you are getting. Now, just so that I will not keep these writings in this slide when I am uploading this. So I've just created another slide for you guys here where I have given that how you will calculate these values. This is just for your reference later on when you are studying in at your home. Okay, so this is for the same question. This is how you find the answers. Okay, but now I want you to find, or I want you to calculate for another question. Okay, so this you will do it in the class. Next question you will do it right now and give me the answers. Okay, so please note, only change in the next question is that you have a bigger packet size, that is 1500 bytes. Okay, header as usual it is of 20 bytes, and as per the previous question all other properties are same. So what are those properties? So let me show you again. You have the bus capacity here. Okay, wait, where is the laser pointer? Yes, you have the bus capacity here, 133 megahertz, 32 bits. That's the PCI bus capacity that you are having because it is a first generation switch. Then main memory bus capacity is 800 megahertz, 32 bits. Then CPU capacity is 300 gigahertz and 200 clock cycles per instruction. Okay, now let's get to this one. Okay, so here too we are just saying that 200 clock cycles per instruction to process a packet's data, right? So if you are sending that header of 20 bytes, that will not be a problem. It will be still done in one instruction itself. So there should not be a confusion in that case. Here only the change that is happening is you have a 1500 bytes packet size with 20 bytes of header. Please find out the values that has been given here. So we have to find the total time to transfer the packet. And finally, we have to find the throughput. At the end, we have another last question. So please find out up to the throughput and then we will get to the last question. Okay. All right, so how do we find this value? Time to transfer from NIC to main memory. So we'll start with the throughput, right? Sorry, effective bandwidth of the bus. So that we know that it is equal to 133 or 133. 133 megahertz and 32 bits. Okay, we know that it is 4.2 Gbps. So what is the transfer time for main memory? We have 1500 byte packet size with 4.2, just a second, Gbps. Okay, it is 1500 byte. What is this value?
2.82 milliseconds.
Okay,
Microseconds.
Microseconds.
2.82 microseconds.
Microseconds.
2.82 microseconds. Great. Then what is the main memory RW time? Do you need to calculate this again?
Same no, ma'am. This
Yes, because 20 byte header. Okay, what was this value in the last calculation?
12.5
Point
nanoseconds.
nanoseconds. Okay, what is the processing time? It should be same, no?
6.7 nanoseconds.
Back IO transfer back from main to NIC. Value to my 8 seconds. What is the total time that you are getting? Please note the
5708.2 nanosecond.
okay. Bring in 1 unit.
Ma'am, you're audible.
Hello. Why is my internet working like this today? Hello, am I audible to everybody?
Ma'am, it's breaking in between.
Yes, ma'am, you are audible.
Okay, to the other students, am I audible? Otherwise, I'll change my
Yes, ma'am.
internet connection.
Yes, ma'am.
Okay, great. So total time,
Yes, ma'am.
how much you are getting? Total time, how
5.7
much you are
5.72 microseconds.
Yes, 5.8 microseconds. I've written it for you. Okay, so total time is 5.72 microseconds. Great. Then, what is the throughput? How much are you getting?
2.1 Gbps.
2.1.
1 Gbps.
Others are also getting this value?
Yes, ma'am.
Okay. So up to the throughput part is done. Now there is the last question. That is, suppose you know your ICs that you have put in your this system, they need 100 Mbps data rate. Okay. So given that the throughput that this system can give is 2.1 Gbps, that is the switch throughput is 2.1 Gbps. Your ICs are basically 100 Mbps cards. Okay, so how many ICs can this switch support? Given that the switch can support only 2.1 Gbps of throughput. Okay, this is a very easy question. The last one, please find out how many ICs can be supported by the switch. Is the question clear? Otherwise, I will again tell this.
21.
21. Everybody is getting 21?
Yes.
Yeah. Okay. All right. So shall I move forward then?
Ma'am,
Yes.
why were we considering the main memory read time twice for the IP header?
It's a read and a write. Okay.
Okay, one read and one write.
Yes. I told it in the last class. All right. So fine then. So please practice such questions. Okay. These will be helpful for your examinations and it will be helpful later on also for clarification of your concepts. All right. So this is done. Then I will get to switching part now. Okay. So I am closing this particular PPT. All right. Is the PPT visible to all of you?
Yes, ma'am.
Okay. Just a second. Okay, so now we are going to get to the new concept which is known as switching. Up till now what we have studied, that switching is basically forming a very important part of when we are trying to route a packet from one port to another port, right? So within the router architecture we do have switching. Okay, with the help of switch fabric we do that. Now why are we doing this? Because we want to transfer the packet that is incoming from a given input port to a particular output port, and we need to do it faster. So we have seen 3 generations of router architecture where one of it used, instead of having a switch fabric, first, it started with a PCI bus. That means if you use a PC as a router, then the PCI bus will be basically in place of switch fabric. You are just using this PCI bus and its bus bandwidth basically to transfer your data. When it comes to the second generation, then in order to distribute the work more to the NICs, you put some forwarding engines inside the NICs itself, and they could do most of the tasks there itself. All right, and then we came with the third generation, where in the third generation it was proposed that why not have a switch fabric. Okay, and there we saw in the third generation that there was a crossbar switch in between the NICs. And why did we use it? Because we were more concerned with um, having more and more paths between the different NICs, and so that more data could be sent at the same time. Okay, so that is why we came up with this. Now in this module, we are going to check about different ways of switching. All right, how can we switch more and more data so that the entire task becomes much more faster? That is sending the packet from the input port to the corresponding output port. Okay, so what do we know when we say switching in computer networks? We know that switching basically means that in the network element that is arriving, that needs to be forwarded to its corresponding output port. Okay, and there are different switching elements. We know that we have telephone switches, datagram switches, ATM switches, MPLS switches are also there. We have studied about all of them. We know that all of them are there, and in details we will study one by one how they work. Okay, so how do we classify switching elements? Okay, so first is that we go back to our packet switching and circuit switching concepts. Okay, so when we want to forward the data in a connectionless manner, then we say that okay, fine, we are using packet switching way of packet switching. When we are using circuit switching, then we say that okay, it is connection oriented. But here in the slide you can see that if for packet switch, it is showing that it can be connectionless or it can be connection oriented. Okay, so you might ask me the question that then why it is like this. For this, I will refer you or give you a hint towards virtual circuit switching. Okay, it is a packet switched network which is virtually using the concept of circuit switch. Okay, so over a packet switched network, it is using the concept of connection orientedness for transferring the data. All right, so this question, that is what is the difference between routers and switches, this is basic computer networks question. I will not ask this question anymore, assuming that you all know about this answer. Okay, at least you should all know about this answer, that what is the difference between a router and a switch. So I have given the answer here. So anyways, we know about router and switches. I will not get into this. Okay, this is a repetition of your computer networks course. Let me go to the tasks of a switch. Okay, so what is the task of a switch? Of course, switching packets. All right, so how does it switch the packets? So it switches the packets after getting all the information from the routing tables. Okay, so the switch also participates in routing algorithms to basically build the routing tables. And as we know from the previous classes, we have seen that when it comes to the situation that there are a large number of packets that are waiting, that are waiting at the ports to be transferred, then there is a question of how do we schedule the packets so that contention can be resolved, either that or simply whatever the packet's priority is, accordingly the packet can be transferred in order to guarantee its QoS that was given by the service provider. Okay, and also one more thing is admission control in a connection oriented network. Okay, so for the last point, I would ask you to just think about this once. How is a switch going to do admission control in a connection oriented network? Of course, we will come to it through this course, but if you can think of it, it will be great. All right, so these are the tasks of a switch. Now let's get to a few more features of it. So how do we measure that, if you are creating a switch also, how do you measure that whether it is performing great or not? You have to compare its some metric with that of another switch's metric. So that metric that is in general used is the switch capacity. Okay, so how do we define this switch capacity? That is maximum rate at which it can move the information, assuming that all data paths are simultaneously active. Okay, so this is the switch, this is the definition of the switch capacity. And what are the requirements then for a switch? So we want, so capacity is the scenario where we are saying that how much maximum amount of data can be transferred by a switch. Okay, so that means given a switch fabric that we have, the requirement is that you should get the maximum capacity for a given cost and a given reliability. Okay, so that means maximum amount of data can be transferred at a given time. The second point is that we want to minimize call blocking and we want to minimize packet loss. I'm sure you all know about packet loss, but call blocking may be a very new term. Okay, so we will study about call blocking in the next modules, but let me give you a very small idea about what call blocking is. Okay, so suppose let us think about the telephone network itself. Because of the term, it makes more sense in assuming it in that way or imagining it in that way. So suppose you are trying to contact somebody else, and or A is trying to contact B, and B is already in communication with some guy C. Okay, so that means the path that you would want to take for communication with A and B is not available right now because B is already in communication with somebody else. So your call will be blocked at that time. Next, another example is that suppose three people are trying to communicate at the same time or trying to call B at the same time. Okay, in that case, what would happen? Only one would get the chance and the rest of the two, they will wait or they will be blocked for that amount of or some amount of time. Okay, so that is also a form of call blocking. Okay, so just get an imagine this kind of a situation. So when it comes to switch, now I think you can imagine that if there is an output port and there are input ports, packets are coming at the input ports, packet can be destined to any of the output ports. Okay, So with that, you can imagine that there can be certain situations where the packet or any packet cannot go to its desired output port due to either that this output port is currently being used by some other input port. That means some other input port's packet is being sent to this output port, or there are some other packets which are in front of this current packet, which which is so therefore it is waiting until those packets are transmitted. Or there are situations that there is no path available from the given input port to the particular output port. Okay, so these are the scenarios where call blocking can occur, and eventually with this packet loss can also occur. All right, so when you want to have a good capacity switch, you need to minimize the amount of call blocking and the corresponding packet loss. Okay, so last point is a very important point, that for a switch only a fraction of paths are simultaneously active. Okay, so which is why switches rarely achieve their rated capacity. Now, why a fraction of paths are simultaneously active in a switch? The reason behind this is that we need to find a path from one input port to one output port depending upon whatever packet is arriving and what is the packet or what is the output port the packet is destined to. Okay, nobody has control over that. All right, so switches, however greatly you make the switch fabric, there will be certain situations where suppose all the packets are destined to a particular output at some time because of some bursty nature of one particular link. So in that case also there will be some blocking happening. Okay, so because of all of these reasons, because of all of these situations or cases that can occur, no matter how great you make your switch, there will be scenarios where all the paths will not be used fully. Okay, so that is why switches rarely achieve their rated capacity. Okay, hope this part was clear. Okay, so now I am coming to blocking. Okay, so this is just a statement that has been given that yes, a circuit switch cannot buffer data. Okay, because there's no need to buffer data in case of a circuit switch. Now, if so, how will blocking occur in case of a circuit switch scenario? That if no path is available from a given input to an output port to carry forward the call or carry on the call, then the call will be blocked, as I was giving you an example earlier. Okay, so that is known as blocking in case of circuit switch network. Okay, now similarly for packet switch network also I have given you some examples. So what we will do is we will see how a generic switch works, and then we will get to see that okay, how different kinds of switch fabrics are there and how do they work, and how there are various ways in which the capacity of the switch is, or researchers try to increase the capacity of the switch. Okay, so now this is how a generic switch looks like. You have the input buffers, these are the port mappers. That is, here you get to know that with the help of all the information that you are getting from the routing and forwarding tables, that whatever the packet has arrived, uh, which output port buffer does it have to go to. Okay, so this is the task of the port mapper. So ingress is basically incoming of packets, egress is outgoing of the packets from this switch fabric. The switch fabric here, it is given just like a black box. We do not know how the switch fabric looks like, but however or whatever your switch fabric is, the task of your switch fabric is that it should route the packet to the corresponding and correct output port, or here, and then the output port will have its buffer. If it's output line is however the output line bandwidth is, accordingly there will be a need for output buffers. Okay, similarly input buffers will also need to input ports will also need to have input buffers, because as I mentioned one example, that there can be scenarios that too many packets are arriving from a particular input port. Okay, so in that case also they need to wait. So where will they wait? For that you need a buffer here. So we have buffers at the input ports also, we have buffers at the output ports also. Okay, and how does the port mapper get to know that which packet should go to which output port? We know that, you know, from the content of the forwarding table, and then, you know, you also need to read the header for the destination, or if you are using virtual circuits, then what is the VCI, etc. Okay, so this is how a generic switch looks like. Now, this is a folded diagram of a generic switch. Now, please remember the diagrams that you had studied in the last class about router, where I had told that a line card has both the input and output ports together, right? It is doing the two of the stuffs together. So if you see this diagram and if you fold this diagram, then it becomes like this. Okay, and these are your line cards. Okay, so this is how your switch basically looks like, a generic switch. You have the switch core here. So this is how we were working, right? This was the way in which the transfer was happening from your line card to the switch card. And then you have your ingress and egress in each of the line cards. Okay, these are acting as different ports. So port 0 to N here. All right, so this is how your generic switch looks like. Now we want to send more and more data at the same time. Okay, so as we know from our basic courses, that how can we send more data at, through the same line, but more data we want to send. Okay, so for that what do we need? We can use multiplexers. Okay, what is the task of a multiplexer? That you have n links, and at the output you can send the combination of this whatever data you are getting over the n links as one output, right? So this is what we know about a multiplexer, and demultiplexer does the opposite. If you have a multiplex data, the task of the demultiplexer is to divide it into the corresponding basic chunks that it was made of. Okay, so this concept of multiplexers and demultiplexers is very much useful in case of, you know, your switch architectures, because, you know, the data can actually be multiplexed here. For example, in case of telephone networks, data is required to be multiplexed. If you remember the first class when I had spoken about you know, circuit switching also, slide or send more and more data together, you can use TDM there, you can use FDM there. All right, so if you still want further more usage of the resources that are already available to you, you can use multiplexer and demultiplexers at both the ends, so that more and more data can be transferred at a time and more usage of the resources can be done. Okay, so that is why these multiplexers and demultiplexers are fundamental to the operation of telephone networks. Okay, so there are various types of multiplexers. So we are going to study first about the synchronous multiplexer. Okay, basic one, it has n input lines, and the output line, of course, it has to be n times as fast as the input lines. Okay, if there are n input lines, of course. All right, so each input line is associated with a buffer, and this will be the sample that we will get once the content of this buffer is put to this output line with the help of the multiplexer. Okay, so suppose let us assume that you have just buffer enough to keep 1 unit of data here, and this is the sample that you are getting, where all of this from the multiplexer, where all this units of data, that is n units of data, are being kept here as a sample. So if you remember the telephone networks, or please remember the telephone networks note that I had given you in the class, where there was one place where I had told that, you know, whenever we are getting the data from a multiplexer, we get it as a sample, and the sample has its starting and an ending, and all the data is in between this sample. And once it gets to the destination side, then the destination will get the data from the, or it will basically get the data out of this sample required data. How does it get it? It gets it in the help of the demultiplexer, whose task is, of course, as we know, that whatever multiplex data we are getting, it will simply again demultiplex it to its different output ports. All right. So this is what your multiplexing and demultiplexing is. And this is an example of a synchronous multiplexer. And the concept of multiplexers is fundamental to the operation of a telephone network. All right. So I have spoken a lot about demultiplexers. Let me see if there's something new in this or not. Okay. We are talking about synchronous multiplexer now. So this is the concept of the same for demultiplexer. So what is the feature for this? We have one input line and n outputs that run n times slower. Of course, they have to run n times slower. And how is that? So you are receiving a sample, no? So the receiving samples are placed in output buffer. Whatever sample is received by this multiplex. Hello? Is there any question from anybody? Or is my voice audible to everybody?
Yes, ma'am.
Okay, okay. So I'll continue. So, yes. So whatever sample is getting arrived at the demultiplexing side, it has to place the values in the corresponding output buffers. Okay, this is done in round robin order. And yes, a multiplexer does not need, a multiplexer or a demultiplexer does not need any addressing information, because the sample itself, you are just getting the sample as whatever is coming from the input port. Okay, so you are not concerned about, okay, we need to know about the corresponding you know, what is the header information, what is the addressing information. Nothing is required. You just need to know that what is the input port, and that will be the corresponding output port for the demultiplexer. So whatever the sample contains as an information, that will be there, that will be required to get what will be the corresponding output port. Okay, so that is the reason for this. And last one is that the multiplex, there can be to carry more and more voice circuits on a single physical line. Okay, so this was an example where only one multiplexer is there. Now you can have more and more multiplexers so that you can carry more and more data. Okay, so this is one thing. Now next we get to inverse multiplexing. Okay, so what happens in case of inverse multiplexing? All right, so what did we see in multiplexing? That there are multiple input ports which are giving some which are pushing some data into the multiplexer, which is at as an output giving a single sample. Okay, now inverse multiplexing should be the inverse of it. Okay, why do we need this? Because aggregation of multiple independent channels can be created with this to get a single higher rate channel. Okay, so you have an inverse multiplexer. What will it give you? It is a single higher rate channel. As an output, it is giving you multiple independent channels. Now you put a multiplexer again after an inverse multiplexer, then you will get a single higher rate channel which will be aggregating these multiple independent channels. Okay, so this is what or how an inverse multiplexer will work. What is its job? That it needs to combine multiple streams, resequencing them to accommodate different variations and delays. Okay, so the inverse multiplexer also allows high-speed virtual links using any existing technology. All right, so this is like you can find out in any books for any example that you get, you will find this out. Okay, so this is basically that. These are very basic terms because everybody told that they are not aware of these things. So I just thought that I'll just put these a little bit, and anyways for telephone networks these are important, so I would have anyways taken these parts. All right, so this is about inverse multiplexing. Okay, let me see how much. Okay, circuit switching, call blocking. All right, so we are almost out of time. I just have only 1 minute left, so I will stop the class here today because I want to start fully from circuit switching from in the next class onwards. Okay, so if you have any questions you can ask me. Otherwise, I will stop the class here only today.
Excuse me, ma'am. Ma'am, in one slide, it was written that we do not buffer the packets in circuit switching. Ma'am,